Hello everyone. My name is Yang. I am a PhD student in the Hong Kong Polytechnic University. The paper I will present today is titled, Behavior Testing of Load Forecasting Models Using BuildChecks. This is a joint work. Buildings are major energy consumers in modern society. In the US, buildings account for over 40% of total energy usage. In another city, like Hong Kong, this value is as high as 94%. In the building, HVAC system is the main energy consumer, accounting for 46% of all electricity used. Recently, with the development AI technologies, the building automation systems have been transformed into information-supported decision-making systems. This provides opportunities to develop data-driven machine learning models for building operation and control. For example, the forecasting model. While developing new models, the researchers would evaluate the models and show their effectiveness. Let's first look at the conventional evaluation methodology in the papers. After the design of model, for example, to design a neural network model structure. The researchers usually split their holistic period of data into train set and test set. After training the model based on train set, they test the model accuracy on the test data set. Finally, they clarify the accuracy on the test data in their paper. Here, we define the accuracy on the test data set as snapshot accuracy. Let's show an example. The left side is AI model developer, and the right side is the model practitioner, such like a building operator, who will deploy the model into real use. The developer public a new developed model, and clarify its high accuracy in her testing data. The building operator would be confused whether he should choose this new model, because he has difficulties in understanding how model behave in usage. For example, if the building operator need deploy the model to work for a new building. He needs time to collect data, hence to train the model. Therefore, before the model deployed, the building operator has to use another alternative solution which could has lower accuracy. As a result, the accuracy in usage is not as good as the developer clarified. That is, model accuracy may change during model usage. In addition, the real situation would be more complicated. Once there are multiple different models available, and all of them clarify high snapshot accuracy in their own test data. It is very hard for the practitioner to analyze which one is suitable for him. Therefore, there are two main problems, while considering deploy the model in real world. The first problem is, although the snapshot accuracy is an important metric, it cannot represent the model behavior and usage. The second problem is, there seems a lot of workload to evaluate the candidate models. In this paper, we present BuildChecks. The goal is to test the in-usage behaviors of machine learning models by behavior testing. Here we bring the concept of behavior testing, from software engineering field. Let's show the definition of behavior testing. It is also known as black box testing. A black box test tests system capabilities by validating the input-output behavior without the knowledge of the internal structure. And we for the very first time, to bring behavior testing to ML models in smart buildings, and defines organized tests. As a result, the users are more eager to understand and compare the behaviors of a wealth of models, without a lot of repetitive programming to test the models one by one. The challenge of developing behavior testing is to define what to evaluate. That is, given a certain forecasting model, what tests we should, or should not, apply to this model. Particularly, there exists different building scenarios. We should justify each behavior tests. In this work, we execute behavior testing on building load forecasting. The goal of building load forecasting is to predict the load demand trend in the future, such like the load demand in the next hour or next day. Load forecasting plays a significant role in HVAC system, and has been widely applied in HVAC control optimization and building monitoring system. Load forecasting researches account for a large proportion in the building research literature. We conduct the behavior testing can help promote these researches deploy in real world. Our contribution can be summarized as follows. First, we propose a behavior testing methodology to evaluate the machine learning load forecasting models. Second, we develop a BuildChecks platform, to materialize our behavior testing methodology. Finally, we use BuildChecks to test the behaviors of a number of models, and we present 2 cases in our paper. Now, we introduce these 3 parts. We define behavior testing methodology from 3 organized aspects. We first discuss the selection of in-usage concerns. As said, in-usage concerns refer to model accuracy change during usage. In-usage concerns have been heavily studied in the AI community. We select 3 typical ones, as cold start, retrain strategy, and catastrophic forgetting. And our methodology can be easily extended. Cold start is: history data needs to be accumulated so that a model can be trained to an acceptable accuracy. This time period is the cold start time. A shorter cold start shows that the model can meet the engineering purposes and be deployed at an earlier time. Second, models face concept drifts in usage and need to be retrained to maintain accuracy. There are different types of retrain strategies, and it is important to figure out the suitable one. Thirdly, since many models have internal mechanism for updating the model parameters to learn new knowledge. Catastrophic forgetting means they may forget existing learned knowledge when learning new ones. We fill these 3 in-usage concerns into the evaluation methodology table. Secondly, load forecasting model categorization. Machine learning models may not face the same in-usage concerns. For example, one model without design with an internal model update mechanism, and thus do not have the catastrophic forgetting concern. To determine what in-usage concerns to test for a model, we categorize load forecasting models into 3 model types which are widely accepted in building automation studies. That is, first one is short-term forecasting with snapshot designs. Second one is short-term forecasting with online learning. And the third one, mid and long-term forecasting. We notate as SSF, SOF, and MLF. Similar, we put the 3 model types in the methodology. Step 3. Based on the concerns from AI community, as well as the load forecasting model type from building studies, we could define the tests. That is, for a certain model type, whether a certain in-usage concern should be or should not be tested. For SSF models, they have cold start and retrain strategy concerns, for figuring out the training data volume needed, as well as how to retrain the model. As they don't discuss how to update the model, catastrophic forgetting concern is not available. For SOF models, besides cold start and retrain strategy, they have the concern about catastrophic forgetting, since the useful learnt pattern should be retained. For MLF models, since they would have a long serving time, and most of them designed with an online adaptive mechanism. Cold start is relatively meaningless. But the other 2 concerns are necessary. We bring in the concrete metrics of the 3 concerns from machine learning community, as well as the related algorithms. Now, we introduce the platform design. We have 2 design goals. Our first goal is to provide automatic evaluation. The second goal is, if the users doesn't have the dataset, we still can serve them. We develop BuildChecks platform to achieve these goals. The user submit the model code file to BuildChecks server, and the server will automatically output the behavior evaluation results, which include visualization and JSON reports. For the first goal, we standardize the user coding format and integrate data, and the corresponding testing algorithms into platform. For cold start evaluation, we design binary search to figure out the cold start time. For retrain strategy evaluation, we implement 3 different retrain strategies. And we implement 2 statistic built-in functions for different online updating strategies. For the second goal, our framework consists of a model testing layer and a building data layer to hold default built-in datasets. For users with their own data, the separation of the building data layer from the model testing layer makes it easy for the BuildChecks platform to be installed directly in their own servers. For users without building data, they can submit their models to BuildChecks, and we report results without disclosing our default datasets. We use BuildChecks to test the behaviors of a number of models, and we present 2 cases in the paper. They are London Residential Model and Hong Kong ICC Model. In this presentation, we discuss how BuildChecks behavior testing on London residential model, since it covers all the three in usage concerns. London Residential is LSTM-based, and it designs an adaptive buffering mechanism to handle contextual adaptation. For the cold start evaluation. While this model has high snapshot accuracy throughout all buildings, BuildChecks reports that in one building this model has a cold start time of 51 days. Yet in another building, the cold start time is about threefold greater. This can lead to a delay in model usage. For the retrain strategy evaluation. BuildChecks illustrates that three types of retrain strategies can significantly improve in usage accuracy in one building dataset, especially periodic retrain. On the other hand, all the retrain strategies can achieve moderate accuracy improvement in other buildings, which is within 6%. For the catastrophic forgetting evaluation. The model in HI building is progressively worse over time. Yet, there is no significant forgetting in other tested buildings. Particularly, during the first 5 updates, not only the model does not forget learned knowledge, but also enhances its prediction capacity. Finally, we summarize our work. In this paper, we presented BuildChecks, a behavior testing methodology, and an associated platform to evaluate the behaviors of machine learning-based building load forecasting models. BuildChecks can output reports on the model and usage concerns, such as cold start, retrain strategy, and catastrophic forgetting. BuildChecks complements the understanding of the machine learning models from the perspective of model accuracy to a richer context. We comment that BuildChecks is designed to provide guidelines on the behavior testing process in smart building, so that models can be comprehensively compared. Clearly, there are different angles to define the testing methodology. It is our future work to investigate other testing criteria. That's the end of my presentation. Thanks so much for listening.